Thank you, Chairman. Today, I would like to present our research about two-dimensional water flow sensor using multiple absolute pressure sensors. We developed a pressure-type two-dimensional water flow sensor for aquaculture. The proposed sensor consists of 6 absolute pressure sensors and uses multiple polynomial regression model. Sensor elements are placed every 60 degrees to measure the pressure distribution. Measured pressure distribution are converted to water flow velocity and direction using a regression model. I will talk about the background. These days, marine environment is changing due to global warming and other factors. A failure to adapt to these environmental changes can lead to fish mass mortality. So, monitoring devices for aquaculture environment have been developed to establish sustainable aquaculture. To meet the need for better monitoring, we developed a two-dimensional water flow sensor. Here we show a conventional water flow sensor for sea current. These sensors were primarily used for marine current research, so these have some disadvantages for aquaculture use, especially the excess presence of marine fouling and particle reduces their accuracy. In contrast, the pressure sensors are less impacted by fouling and particle. These are the sensor requirements as shown in the table. We determine sensor measurement range and resolution based on the characteristic of fish farm. I'd like to explain the measurement principle sensor. The relationship between flow pressure and velocity is understood to be squared based on Bernoulli's principle. To measure the flow direction, we consider a pressure distribution around the cylinder in a uniform flow. Without considering viscosity, a pressure distribution can be represented by this formula. However, when considering viscosity, it cannot. So, in this research, we use multiple polynomial regression to model pressure distribution. The measurement pressures are compensated by subtracting the pressure caused by static water and inclination. After this compensation, the multiple polynomial regression model takes 6 pressure values as input and produce 2 values related to the water flow as outputs. Then these outputs are converted to velocity and direction using these formulas. Now, I would like to explain the design of the proposed sensor. The features of the proposed sensor are cylindrical housing, the use of 6 absolute pressure sensors, and the use band-shaped flexible printed circuit called FPC. By using the FPC and absolute pressure sensors, the fabrication process becomes simple. These are the components. These components have features and functions as shown. The pressure sensor element is waterproof and has temperature compensation function. It measures between 1 to 200 kilopascal with resolution 1.6 pascal. Due to the use of multiple sensor elements, we use a multiplexer. This multiplexer resolves address conflicts. The converter board transform lines from FPC into through-hole vias. The cylindrical housing are made by aluminum machining. The band-shaped FPC are made to align with the inner diameter of the housing. Next, I'd like to explain the fabrication process. First, we wired and connected the converter board and I2C multiplexer together. Next, simultaneously solder pressure sensors onto the FPC using hot plate. Following that, we bent the FPC and inserted it into the housing. Next, waterproofed around the sensor element using UV curing resin and UV light. Afterwards, we connected the converter board and the FPC. Lastly, we injected epoxy resin to waterproof inside. Here we show the photograph of the fabricated sensor. It can be confirmed that all components are waterproofed. For testing the response of the fabricated sensor in Waterflow, we conducted experiments in the circulating water tunnel with a rotation stage. Here are the conditions for this experiment. This graph illustrates pressure response of each sensor elements to the water flow. This graph shows at when velocity 0.8 meter per second. This shows 1.2 meter per second. We can confirm that pressure distribution varies based on the flow velocity and the direction. We took the average of 100 data points per condition, then conducted regression model construction and estimation. The experimental conditions are referred to as a ground truth. This graph illustrated the fitting of the estimated value to the ground truth. Using these outputs, calculating velocity and direction. This graph shows estimated velocity compared to ground truth direction, and this graph shows estimated direction to compare to ground truth direction. We evaluated the accuracy of the regression model using root mean squared error, RMSE. The RMSE is an evaluation metric for the error between the estimated value and ground truth, as represented by this formula. These graphs show velocity RMSE and direction RMSE compared to ground truth velocity. We can confirm that sufficient accuracy are obtained. Next, we conducted experiments for inclination compensation. Pressure differences caused by inclination are represented by these formulas. We computed using these formulas by inputting values given under experimental conditions. Here is a photo of setup inclination compensation. We use goniometer stage to incline the sensor. We test three inclination conditions, inclination 0, 10, and 20 degrees. These graphs show the pressure response at each inclination angle when the velocity equals 0 meter per second. We can confirm that the pressure difference is due to the inclination. These graphs illustrate the root mean square error for each inclination angles. At 0.4 meter per second, pressure due to the inclination becomes significant in the measurement pressure. The compensation was not adequately performed. However, we can confirm the effect of inclination compensation in the high-speed range. Here we summarize in conclusion. We propose the waterflow sensor consists of 6 absolute pressure sensors and using multiple polynomial regression models. The fabricated sensor meets the required specification in the high-speed range for a regression model with inclination angles. Thank you for your attention.